Hello, community! So great that you're back. Yes, today we discovered that an AI can sync in images. And you might say, this is amazing, so do we have something like a visual chain of thought now developed? Well, you are not gonna believe this, but yeah, Nvidia, MIT, and Stanford University, they came up with a brand new idea and they framed it as a visual syncing. So let's have a look. I mean, it is a pure coincidence that just yesterday, I ended the video where I said, hey, visual reasoning, anybody, any idea how to make it visual? And today in the morning, we have a new publication by Nvidia, Stanford, and MIT. So let's have a look. Let's have here a spark of genius. What are they doing? They want to enable here an autoregressive transformer to speak images in the same way that a transformer can speak text linguistic information. So they have now a transformer that processes here or generate here the next token, an autoregressive transformer can do so whether the token is a word or a codebook index. Now you know codebook indexes if you're a subscriber because I just showed you this here about new foundation model and I told you, we can work with diffusion transformers here in Nvidia's Groot N1 to have some robust actions, and we have flow matching and whatever. And I showed you then in detail in step 1 here, we will use here a vector quantized variational autoencoder methodology where we have now our autoencoder, and then I showed you here the specific loss function, how to calculate it, how to code it, and how to compute this in particular. But let's come here to the core new idea. Yes, we will use here a vector quantized here variational autoencoder. This is the technique. So if you are not really familiar here, a 5-second refresh. We have an encoder network that takes here a raw image, let's say 256 times 256 pixels, and outputs here a two-dimensional feature map of a continuous vectors. For example, we have 16 times 16 features, each of a particular dimension D. Then each of these 16 times 16 continuous feature vectors are quantized to the nearest entry in a learned codebook. Codebook is nothing else than a specific collection of embedding vectors. And the index of the match codebook entry is called a latent token. So if your codebook has, let's say, 8K possible entries, so each patch in your 16 times 16 grid gets replaced by just a single integer. So beautiful. We have a beautiful embedding happening here in our vector space. And then, of course, this is the encoding, and a decoder network can do just the reverse. So what is so nice? Oh yeah, I gotta remind that last time I said latent token because in German, it is latent. But of course, in English, when I go here with the British pronunciation, I put this here as a reminder that it is a latent. So the latent token are simply the integer indices in the learned codebook. So we just have, if you want more or less indexes or token or a latent token, doesn't matter at all. We can calculate it in an autoregressive transformer. And we do not need a diffusion transformer, which is great. So of course, here now we really depend here on the training data. During training, variational autoencoder here, it learns here this codebook that captures now these recurring visual features that we want to map. And for instance, one code might present here a bright red round shape, while another represent here an edge of a table or whatever features you have in your particular training data. So the training data become now really the most important source of high quality information. Yeah, if you're under encoder in a vector space, discrete indices, a little bit more information if you're interested in. But just want to show you this. Now, this is amazing from Nvidia. Now, what we have a start condition like this one here. Now, we have here a verbal instruction, put the carrot on a plate. So you have here a sink, and here there's a carrot, there's a robot, and there's a kind of a plate. And now what we have to do, I don't know, every 2 seconds or every sequence, we have now to generate, if you want, syncing images. You see, it comes down, grabs the carrot, moves the carrot over the position of the plate. And if it's really over the plate, it will release here the carrot on the plate. So this sequence here, we have here, if you want, the beginning, and this is here the end. And now we generate here syncing chain of thought elements. So this means we have to have, I don't know, depending on the resolution of your images, I don't know, 200, 400, 500 times 500 pixels images that we have to generate for this visual thinking, this visual chain of thought thinking till we reach here the end. So our system now has to be able to generate those images, those visual thinking steps. Now, we do have a beautiful study from Nvidia, from Stanford University, and from MIT, as I told you. Beautiful, great consortium from March 27, 2025. And they tell you here exactly this is what we do, and you have a GitHub. But let's look at the model. Now, interestingly, the model is a real simple one. Because they say, you know, we want to be fast, we want to be inexpensive here for our robotic training infrastructure. So maybe not go with the maximum capacity that we have, but let's have a look here at a chain of thought vision language action model. Great. Now, this is more or less really the core. This is the core idea. This is all you need to know about this paper. So they tell you here for this chain of thought vision language action model, the new model, the key insight is to incorporate explicit visual reasoning before the action generation. And you know, the action is how to program here the arm of the robot to pick up the carrot, how to control the actuators, all the different motors here on this robot arm. And they say, so before we do this, before we generate the action, we want to see here the visual steps that the arm should perform. How do you do this? They have two phases. At first, we predict here a sub-goal image, let's say 2-3 frames ahead, as the intermediate visual reasoning step. And then, if we have these intermediate visual reasoning steps, then we generate a sequence of M actions to achieve this sub-goal. So then the model learns how to have these actuator actions for the robotic arm. They say this enables now the model to think visually first, by explicitly reasoning about the desired future states before now predicting the action. So you see this visual reasoning step here, this chain of thought step, this is so important because this is now important here on the training data. And they say we have robot demonstration where a human guides here the robot here precisely to later imitate the action here, and they have action-less videos. So the robot just have a video, but not here the commands for its actuators on the robotic arm. And now the idea is that we train now an AI system so that the AI understands what are the sub-sequences, what are the subgroup images that I have to generate before the thinking can happen. Now you might say, hey, wait a minute, just less than a week ago, you showed us also from Nvidia here the Groot N1 and the Reason 1, the physical AI understanding. Absolutely. But look at this complexity. If you want, these are the big brother models. This is Nvidia pure. No? This is what Nvidia offers its customers, industrial commercial clients. This is real expensive, real huge infrastructure. What we have, just look here, I showed you in my video here, the technical specifications of N1. For the model architecture class, we have a vision language action model, beautiful. But just for the vision encoding, we have a SIGBIP2 encoder. For the linguistic reasoning, we have a small LM2 language model. For the action generation, we have a complete diffusion transformer. For the annotation of data, just for the annotation, we have a vector quantized variational autoencoder. For the optimization, we have a complete mathematics that I showed you in the video about flow magic loss function that are highly specific, and then the optimal number of interaction if you run the inference, and turns out it is to be 4. If you don't want here to start up this huge, humongous compute infrastructure, the idea is simple to go with something cheaper. However, this here has some huge benefit for industrial application. No? Let's say you are somewhere here in an environment, let's say this is just a simplification of a kitchen. and you want to take something out of the fridge and want to put it here on the plate on the tabletop. So what you do with this pure NVIDIA models, you have, let's say, a LiDAR system. So you know exactly where you are standing as a robot, what is the distance to this, what is the distance to this, and you can calculate now if you want an arm movement in absolute coordinate terms. So you have to go from here and you have to move your arm over there. You only can do this if you do have the exact distances, the exact rotation, the exact frequencies, and so on. But if you don't have this, what you do? You go, and this is now from this paper here, step by step. So you use a visual chain of thought reasoning here in a very particular way. So again, the pure NVIDIA, they have LiDAR system, visual system, point cloud systems. So extreme precise movement. They know exactly in the three-dimensional room where they are. Where's the robotic arm, where to pick up something. So their LiDAR data alone gives them here an absolute precise feeling here for distances. In this new study, the topic of today, we don't have LiDAR systems. We just have vision systems. And now those vision systems, as I told you, maybe you have 256 pixels times 256 pixels here. If we go with the standard VLA that they used here in their study, you don't have this precision. And you have just here a visually distorted image, no? Because you can judge how the depth here, the depth information is missing in your kitchen model. So you have this, no? This 16 times density grid of latent tokens, and then the system tries to make sense out of this. So therefore, we cannot just calculate the movement of an arm from the fridge to the table, but we have to go tiny steps by tiny steps by tiny steps by tiny steps. So if we make a mistake here in the control here of the actuators of the robotic arm, we just make a tiny mistake and we can immediately correct it with the next video stream from our sensors. Think about, think about in the internet, I've seen a video. If you have a car, like a Tesla, that is based here on visual data, not on LiDAR data. So just has visual cameras, multiple of them, can calculate some beautiful things. But if you compare this in some critical situation with cars that have a LiDAR system that can measure distances in their environment on centimeters, plus or minus 1 or 2 centimeters, you know, this is a different system, and they can work with different methodologies and with different precision. But today we talk about this little model here, Nvidia, Stanford, and MIT, and you understand that Nvidia is here so much interested in this because this is, if you want, small, quick, fast, and a little bit dirty in the implementation, you know, but it's cheap. You can offer this a different sort of market players. Your next clientele, if they're not able to pay your prices here for the huge software implementation and hardware implementation, you can maybe go for something like this. So just give you the correspondence here. Yeah, for the model, I just wanted to show you, they have here, as I told you, 2 stages. They have a pre-training stage and a supervised fine-tuning stage here. And just as you expected, the pre-training stage here, pre-trained on a large-scale vision and language data before being tuned on the pure robotic task. So we use here a model, I'm going to show you this in 10 seconds. It's pre-trained on image text pairs, on video text pairs. And this teaches you the transformer how to convert images, two-dimensional distorted images, as recorded by its video cameras, into some latent tokens in our latent space, in our embedding space, and how to generate images here in an autoregressive manner. Just to give you an idea, Nvidia tells us it took about here only the pre-training 11,000 A100 GPU hours just for the pre-training. 11,000 hours. And you have to have the data. No? You have to generate this data. So the quality of the data is so important. So, and then, yeah, if you pre-train the system, 11,000 hours. The supervised fine-tuning is rather simple, no? Because now, more or less, you're only focused on the robotic demonstration data. So you have the final specialized data set here the action sequences where the human guides now a robotic arm and helps here really the system to understand each micro movement in detail, supervised fine-tuning. But here also this model refines the ability to generate our sub-goal images that correspond now to the actual future state here in the robotic demonstration, as I just showed you here moments before. So you really have to generate the sub-goal images. And yeah, I guess Nvidia can use here synthetic images, because otherwise this would take, I don't know, months or years to generate those real-time data where the humans guide here the robotic arm here for each and every form and shape and color. So with the supervised fine-tuning, the system learns how to generate here the correct robotic actions. Great. Let's see. The model, as I told you here, that they use here is a 7 billion vision language action model that they already developed 2 years ago. And they say, if we compare now here with our specific 2 steps pre-training, if we implement our idea now of our visual chain of thought reasoning, then our model here, the 7 billion vision language action model, is up to 17% better, has a better performance than if you go with the standard non-implementing our idea vision language action models. And they tell us, the core innovation, if you want, in this paper, if you have it just in one sentence, is the sequential generation of a sub-goal image. So you really provide image representation of how you want a process to continue, followed then by an action generation, your actuators, how you control your actuators on the robot, condition on that particular sub-goal. So you don't go here and make a huge sweep with your arm, but you go tiny steps, correct, tiny steps, correct, tiny steps, because you don't simply have, for example, the LiDAR data, the absolute distances. So you have to be real careful if you only go with visual data. And this forces here, if you want the AI model to visualize an intermediary goal before acting. And you can have here verification runs and whatsoever. But I just wanted to give you the main idea. I wanted to show you what is the core of this new idea by Nvidia, Stanford, and MIT. How does it relate to the huge commercial Nvidia vision language action model where we have the world models? Well, this is a tiny little, quick, fast, a little bit dirty, but otherwise very interesting procedure, and it achieves up to 17% performance increase. Yeah, the model. This is the publication for the model. I don't know if you're familiar with this. This is already here, the version 3. This is from March 2025. And you have here the GitHub. So go there. It is from Tsung-Yi University, MIT, Nvidia, UC Berkeley, and UC San Diego. Some real interesting model. They build about, they call this here the VILA-U model. U, of course, for Unified Foundation Model. And VILA for Video Image Language and Action Model. Unfortunately, a very low resolution, only on 256 times 256. But maybe Nvidia has some other internal model it has not published yet. We've seen here from our colleagues in China, they go already to a 4K resolution. Beautiful. So you see, we are moving here completely here, Unified Foundation Model. And here one of my last videos was here on the World Foundation Model. So we are moving with our AI out in the world, out in the robotic system, out in the interactive physical AI system. And this is from MIT, Nvidia, Berkeley. Everybody is going out, wants to have an interactive in a physical world AI system. Great. So there we have it. Complete learning process is here rather simple, just this 2-step process. We have the pre-training, 11,000 hours on a large vision and language data set, and then a supervised fine-tuning for the pure robotic demos. This is it. This defines our action if you do this, and if you have the training data, and if you have the infrastructure here for the pre-training, this is it. This sub-goal image is so interesting now, because you can compare this to the way we use our words here in our chain of thought. And now the sub-goal image is our visual chain of thought equivalent, if you want. So if you want that a system thinks not in a diffusion transformer model, but in an autoregressive transformer model, you understand it is already a simplification. No? This shows you that Nvidia is not going with full-fledged high-level technology, but they say, yeah, you know what, autoregressive. So I don't mind if it's a text token, if it's an image token, if it's a codebook token, just go with it and we can be quite fast, autoregressive, and it's rather cheap in the implementation. Beautiful chain of thought, vision, language, action demonstrates here that it's working. The step-by-step visual reasoning is really working. It improves our robotic manipulation up to plus 17%. So this is a real nice study, not complex, not huge infrastructure. Chain of thought, vision, language, action model, a novel visual chain of thought approach for some real fast robotic learning, merging here our subgoal image reasoning with the short action chunk generation. I recommend this study if you really want to learn something about it. They have a ton of video data also on their side. So if you want to see all these training videos, there's a lot of data and a lot of performance comparison. But if you understand the main idea, this was the most important step for to understand, hey, how is it possible that our AI system now think in images? And this was not possible if you want just days before. And now, the next day, we already have a new AI research paper by Nvidia, Stanford University, and MIT. I hope you enjoyed it. I hope you found some new information. If you like it, hey, why not subscribe? And I see you in my next video.